So far this week, we've been discussing four different problems, which were sort of in pairs of similar problems. We talked about this two-sat problem and the very similar three-sat problem, and we talked about the shortest path problem and the longest path problem. So two-sat and three-sat both said, given a formula, can we find a way of assigning true or false to the various variables in that formula so that the whole formula was a true statement? The only difference between those two, between two-sat and three-sat, was that we were going to be expressing our formula in a particular way, and for two-sat, that formula could be expressed as what we said a 2CNF formula, where we had these clauses where there were ors within a clause, and two variables that we were oring together for two-sat, and then for three-sat it was three variables we were oring together. Shortest path and longest path, we're both concerned about finding paths from a start node to an end node in a graph. For shortest path, our goal was to find the quickest way to get from the start to the end. For longest path, our goal was to find the longest way to do that. And these problems sort of ended up fitting into these two categories, where two-sat and shortest path belong to this class P that we said were the problems that were maybe easy to solve. And by easy, we mean that a Turing machine could compute them in polynomial time. So we could solve those problems in polynomial time. On the other hand, three-sat and longest path belong to this class that we called EXP, short for exponential. And these seemed, at least, to be hard, where the best known solutions we had for these problems was one where we essentially had to try all of the possibilities. So note that we didn't say that it definitely was going to require checking all the possibilities to solve three-sat and longest path. We just said that nobody at this point in time knows of any better solution. So these are sort of in this gray area where we don't really know if it's easy for us to solve them in polynomial time, or if it's going to be easy for us to solve them, meaning we can solve them in polynomial time, or if they actually are going to require an exponential time solution. So something to point out about the relationship between these two classes, P and EXP, we definitely know that P is a proper subset of EXP. So we know that there are some problems that can be solved in exponential time that absolutely cannot be solved in polynomial time. However, three-sat and longest path specifically, we actually don't know if those are an example of such a problem. So we don't know if three-sat or longest path absolutely require exponential time, or if there is some way of solving them in polynomial time. So the reason that we're sort of a little bit shaky about three-sat and longest path, we're just not quite sure whether or not they do belong in P, and we can't prove that they don't belong in P, is that they fit into this other category of problems that has some really interesting properties, and that is this class NP. So where P is the category of problems that are easy to solve, we can solve them in polynomial time. And exponential time, EXP problems are the ones that can be solved in exponential time. NP is going to be all of the problems that are sort of easy to check in polynomial time. So basically the idea for NP is that if we had some potential solution for let's say three-sat, then we're going to be able to verify the correctness of that solution in polynomial time. So for instance, if you gave me an assignment of true-false for each of the variables, I could easily, that is in polynomial time, check whether that assignment you gave me was actually a satisfying assignment. And for longest path, if you gave me a path from S to T that was of a certain length, I could check that that was going to be a path of at least length n that went from S to T very easily. I could just follow that path to make sure it was a valid path from S to T in the graph and check that its length was long enough. So NP problems are the ones that are easy to check, is sort of how we intuitively think about that. Formally, though, we define the class NP as all of the problems that are going to be solvable in polynomial time using a non-deterministic Turing machine. So the N in NP stands for non-deterministic. So NP stands for nondeterministic polynomial time. So P stands for polynomial time, NP is nondeterministic polynomial time, EXP is exponential time. And we don't know the relationship between NP and P. We don't know whether or not it's possible to take any problem we can solve with a non-deterministic Turing machine in polynomial time and convert that into a deterministic Turing machine that's going to run in polynomial time. So we definitely know that NP is going to be a proper subset of EXP. So just like we knew that some problems belong to EXP but did not belong to P, we do know that there are some problems that belong to EXP that don't belong to NP either. What we don't know, though, is whether or not P is a proper subset of NP. So we don't know whether or not there are some problems that can be solved in polynomial time using a non-deterministic machine, where there is no way to solve them in polynomial time using a deterministic machine. We definitely do know that P is a subset of NP, perhaps not a proper subset, but we do know it is a subset, basically because nondeterminism is a superpower. So any machine that is deterministic is sort of a special case of a nondeterministic machine. So every problem that belongs to P also belongs to NP, but what we don't know at this point in time is whether or not there are some problems that belong to this class NP that do not belong to the class P. So let's review a little bit about what nondeterminism actually means before we carry on. So we talked about nondeterministic finite state automata, or NFAs, where the idea was that for NFAs, when we were looking at our input, the machine could be defined in such a way that once we received some input character for us to transition on, there was a choice to be made. So a deterministic finite state automaton, there is only ever one option for what we could do next, for which transition we could take. For a non-deterministic finite state automaton, there were choices available to us. So in this instance, if we were in state 1 and we received as input a 0, there is a choice for where we could go next. We could either stay in state 1 and follow that self loop, or we could advance to state 2. So DFAs, or determinism, means there is only one potential choice to make for what to do next. Non-determinism means we might have multiple choices available to us. And we talked about two different ways that we could sort of think about non-determinism, or how a non-deterministic machine is going to behave. We could think of a non-deterministic machine as being very powerful, so it could have this idea of omnipotence, additional power, where it has this extra power to be in multiple states at the same time. So we could think of it being in state 1 and state 2 simultaneously, so in parallel. Or we could have thought about it as omniscience, where basically we could think of the machine as being able to make really, really good choices all the time. So if it was in that state 1 and we received a 0 and wanted to know if we should do the self loop to stay in state 1 or advance to state 2, omniscience is basically saying the machine, when there are two choices given to it, it always picks the best choice. It always picks the choice that's going to allow it to end up in an accepting state. So whenever there's multiple choices, we're just going to say that whatever one is going to eventually work out best, the machine is just going to, as if by magic or wisdom, always pick that one choice. When we look at non-deterministic Turing machines, it's going to be the same story. So non-determinism in Turing machines means that we're going to have multiple choices for what we could do next. But the difference is that we have not just states to worry about with Turing machines, but we also have the tape. So here might be one component of a non-deterministic Turing machine would look like, where you can see that on state 1, if we are looking at a 0 on the tape, then one option might be that we write 1 to the tape and then move our position on the tape right by 1 square. Or another option, if we're looking at a 0 on the tape, is we could leave that 0 there and then move our position on the tape 1 to the left. So something like that. So here we have two choices. This is a non-deterministic Turing machine. And depending on which choice we have, or which choice we make, we could have not only two different states that we're in, but also two different ways that the tape could look. So we could have two different states and two different positions on the tape and two different entire tape contents as well. So if we're looking at a 0 on the tape and we take the self loop, we'll end up in state 1. We'll end up with a 1 at that position where there was previously a 0, and then we've moved to the right. Our other option was that we could have advanced to state 2 and then not change that position on the tape and then moved our tape position 1 to the left. So in this situation, we don't just have two states to look at, we actually have two different machine configurations that we need to keep track of. So non-determinism with Turing machines is going to be a little bit more complicated than finite state automata. When we were talking about non-deterministic finite state automata, we said that those were not going to be any more powerful in terms of computability because we could do this power set construction, if you recall, where we could take our non-deterministic machine and convert it into a deterministic machine by saying each state is going to represent a set of states in that non-deterministic machine. So that was that power set construction. We can do a similar thing for non-deterministic Turing machines, where we're going to be able to convert non-deterministic Turing machines into deterministic Turing machines. However, what we're going to see is that the method of this translation could cause the Turing machine to take a lot more time when we do this. So just to recall the execution model for a traditional or deterministic Turing machine, basically what we would do is we would just say over and over and over again, so keep repeating this process of applying our transition function in order to figure out what is going to be the next state that we're going to be in our machine, what character should we write to the current position of the tape, and then some sort of tape instruction about how we should move on the tape. And then what we do is we write the character that we were told on the tape, we move to the next state that we were told to move to, and then we do to the tape what we were instructed to do, where one of those options was to halt. And then once we had halted, then we sort of break that repetition, and now we know what to return, where we're going to return a 1 if we ended up halting in an accept state and 0 otherwise. So that's how a deterministic machine worked. The difference with a non-deterministic machine is that when we take our transition function, there is not just one next state or one character to write or one tape instruction. There actually might be a set of those. There could be several different combinations of those choices. So for a non-deterministic machine, what we're going to do is we're going to sort of introduce a for loop here. We're going to do this same process, but for each of the configurations that our machine could have been in parallel. So we're going to repeat over and over and over again for every single configuration. So we've added this for loop for each of the configurations the machine might be in. And then for each combination of next state, character to write, and tape instruction that we're going to get from our transition function, we're going to do all the same things a deterministic machine would do. So we're going to write that character to the tape, move to our next state, and then obey that tape instruction over and over and over again. So for each configuration, for each thing we could do next, we're going to make that change and then add that configuration to some sort of collection of configurations. So now the main thing that's going to be different here to pay attention to is how exactly is it that we're going to be halting with these machines. With a deterministic machine, it was easy. Once we followed some sort of halt transition, then we just stopped. For our non-deterministic machine, since we have all these different configurations that are floating around that we have to deal with, what we're going to do is we're going to say that if any of the configurations halt and accept, then we stop all the other configurations. So for a non-deterministic machine, we have these two, it's the same as a deterministic machine, but with two added for loops, where we say for each configuration, for each thing to do next, for each choice of things to do next, we're going to write stuff to the tape, move to the next state and obey the tape instruction. If that tape instruction caused the current configuration to halt in an accept state, then we stop every single other configuration. Otherwise, we're going to keep going. And then we're going to, at the very end, return 1 if any configuration ended in an accept state, and 0 otherwise. So now we can see kind of that we could definitely write a Python program that would evaluate this non-deterministic machine that we see on the right. So we can add for loops to a Python program that might be trying to simulate a Turing machine. So with this pseudocode that we have on the right, hopefully you can be convinced that any Turing machine, any non-deterministic Turing machine, could be simulated by, say, a Python program and therefore a deterministic Turing machine. However, it could take a lot more time to do this non-deterministic Turing machine, because for each configuration, we could have multiple potential next configurations, causing this exponential blowup in the number of configurations that we need to keep track of. So for a non-deterministic Turing machine, if it has these powers of either omnipotence or omniscience, then it can be more efficient than this deterministic Turing machine. So the omnipotence idea for non-deterministic Turing machines essentially says that we're able to do multiple configurations in parallel. So the machine could be in multiple configurations at the same time, or it could be working through multiple configurations in parallel. So that the amount of time it takes for the machine to advance one step in its computation is going to be the same regardless of how many configurations the machine happens to be in. With omniscience, it basically says whenever there are multiple choices for what to do next, multiple next possible configurations, the machine is always going to pick the right one, the one that's going to cause it to accept if that exists. So with either omnipotence or omniscience, the non-deterministic Turing machine, at least intuitively, seems like it should be a lot more efficient than the deterministic Turing machine. So intuitively, we think this is the case, but so far nobody has actually been able to prove that it requires exponential more time for a non-deterministic machine that's been converted into a deterministic machine to run. So it requires exponential additional time to convert a non-deterministic machine into a deterministic machine. So this idea of omniscience is actually going to give us a shortcut to thinking about these non-deterministic machines. So this idea of omniscience said whenever there is one choice to make, our non-deterministic machine is always going to pick the choice that is going to take us to acceptance the quickest, is basically what omniscience does. And essentially, the way that we're going to be thinking about this omniscience idea, is we're going to say whenever there is some choice to make, let's say that the Turing machine has some directions for which choice ought to be the right one. And this list of directions, we're going to give this label as a witness. So if we had a deterministic Turing machine that had access to the cheat sheet of all of the best choices to make in our Turing machine, that is, whenever there were multiple options, if we had some cheat sheet that told us which option was the best option to make, then now it's not actually going to require any more time for our deterministic machine to run compared to the non-deterministic version of that machine. So with a little bit of extra information, so with this witness or this cheat sheet about which choices are the best choices, we can actually convert our non-deterministic machine into a deterministic machine without using any additional time. And this idea is going to be the way that we're going to be thinking about this class NP. So recall the class NP was the set of all problems that could be solved by a non-deterministic Turing machine in polynomial time, which we could also think of as the class of all problems where we could have our cheat sheet of choices that allowed us to verify true instances of that problem in polynomial time, in deterministic polynomial time. So the class NP is going to be the set of all decision problems that can be solved in polynomial time by some non-deterministic Turing machine, or equivalently, the set of all decision problems where the one instances of that problem, so that is inputs where the output was going to be 1, can be quote-unquote verified in polynomial time given this witness or this cheat sheet of choices to make. So as an example of how this cheat sheet or these choices are going to be useful, for 3-sat, we can show that 3-sat belongs to this class NP by saying that the witness is going to be some potential candidate satisfying assignment. So if we're given some 3-sat formula, some 3CNF formula, and we want to know whether or not that formula is satisfiable, there exists a witness that we can provide that would help us to verify that solution, that formula to be satisfiable, provided that it is. And that witness that we could pick is maybe a candidate satisfying assignment. So if I hand you a 3CNF formula and an assignment that satisfies that formula, you can verify the formula is satisfied by that assignment in polynomial time by basically just plugging in all the true-false values and evaluating that formula. So this actually proves to us that 3-sat belongs to this class NP, because whenever a formula was satisfiable, we could find some witness for that formula, that being an assignment which does satisfy it. Since we can verify that assignment in polynomial time, 3-sat belongs to NP. For longest path, our witness could have been an example path of length n that went from S to t. So given a graph, a start node S, an end node t, and a number n, if you gave me a witness being a path from S to t of length n, I could verify that witness to be a valid path from S to t of length n in polynomial time, allowing me to verify that the STN instance for that graph was true. So since true instances can be verified in polynomial time with access to this witness, we can show that longest path belongs to this class NP. So in summary, we have these 3 classes, P, NP, and EXP. P are all of the problems we can solve in polynomial time without access to any additional information. NP are the problems that we can solve that we can verify in polynomial time. So if you gave me an instance to the problem and maybe a candidate solution to the problem as well, I could verify that solution was correct in polynomial time. And then EXP are the problems where we can solve in exponential time. And now what is probably the most important open question in all of math and computer science right now is this question of whether or not P is a proper subset of NP, or whether or not they are actually the same set.